Shamik is not around, right? I don't see Shamik over here yet, but oh, there you go.
All right, I'm ready to go.
All right. Welcome, everybody. This is great to see everybody here. Let me share my screen in here. Give me 1 second here. To copy. There we go. All right. Yeah, thank you everyone for joining us. The release is out. Gazebo Jetty is out. You can go check out the announcement on this discourse post. I don't want to go through all the details, but first and foremost, I want to thank to more than 100 contributors who made pull requests that are merged into Gazebo. Thank you so much. This couldn't happen without you, so we're so grateful, and we're also grateful for everyone that participated in the tutorial party. We had 25 participants outside of the core Gazebo committers group, and we ended up closing 68% of our total issues. And here are some of the stats about which platforms we closed. But even more important, we had 74 PRs opened out of because of all of the issues we found during the tutorial party, which is great, which made Gazebo Jetty even better and more stable. You can click on this link to see the tutorial party leaderboard that has all the participants, and again, thank you for everyone that participated in that. We'll do that again next year, so keep an eye out for that. And looking ahead, the new Gazebo, the next one is called Gazebo Cura. So we had a voting that happened over discourse, and I think we had over 60 people voted. I didn't check last how many people, but this was a ranked choice, and so Gazebo Cura won. So thank you for everyone that voted. And now we have one sort of action item, call to action here. We're working on the roadmap for the next for Gazebo Cura. And so we would like to hear from you. We have a survey out that was posted last week, and it'll close in a couple of days. I think Friday is the last day. So if you want your voice heard, please fill this survey. We're going to use it to inform what we do in this release cycle. And that's all I had. We had a lot of things packed up for today. So I'll hand it off to Ian.
All right, thank you everyone for coming. So we have a lot to go through today, like Adisa said. So this is all the work that we've been doing in the past year. A lot of these features that we are going to show today are in Jetty, and many of them have been backported to Ionic and maybe Harmonic as well. We have altogether 14 demos to present, ranging from physics, new plugins, transport, packaging, and also there's going to be a more complex demo at the end involving integration of ROS, Gazebo, and OpenRMF. There are 10 presenters here, so bear with us. We'll be switching from screens to screens. But as usual, we will start by introducing the demo environment. So every year we create a new demo environment to go with our release. In the past, it's been a cafe environment, lake house, a fortress, etc. And I will share my screen right now. Let's see. Just to show the demo world today. All right, so this is the new demo world, and I would like to introduce you to Cole, who created this beautiful demo world. Cole, take it away.
Thanks, Ian. Yeah, hi everybody. I'm Cole. So yeah, as Ian mentioned, I helped create this environment for the Jetty release. So I'll be talking a little bit about that. So this is like a large distribution warehouse with a few different assets you can play around with. We have some pallet racks. Oh, it's the red and gray shelving there for holding pallets. We have picking shelves for bins and smaller items. You can see some other miscellaneous assets around like ladders and pallet jacks and things like that. We also have these packing stations for, this is where people would box things up. And then the loading dock, excuse me, in the background there for actually loading things onto containers. So, and like I said, just like some miscellaneous things, you can see a dolly there, and there's some stuff up against the wall as well. We are also, all of the colliders in this scene are primitive colliders. So you can see on this forklift model, we're just using simple shapes to approximate the collision. So this is good for physics performance. And yeah, all of these models can be found individually on Fuel as well as the world itself is up there. You can see we have the same sort of collision set up for the packing station, and this is the same for the entire environment, including the walls and floors and everything like that. So yeah, all of these models were set up in Blender. I'm going to take over for a second here, Ian, and
go ahead.
show a little bit how we set up these models. So this is we do this in Blender using a tool I made called SDFGen. So this lets you quickly set up models for Gazebo. There's a bunch of utilities that'll clean up meshes. You can set up links. You can set up colliders very quickly and easily. So this is how we build out all these simple shapes really fast. You can set up joints, materials, lights, and then you can finally export all that out with SDF, any mesh colliders, config files, all that fun stuff. So that makes it really easy. So this is all up on GitHub. I'll throw up a link in the meeting notes. And yeah, Ian can take it from there.
All right, thank you. So that's the demo world, and then we're going to switch to Adisu, who's going to talk to us about GUI and standard simulation interface.
Thanks, Ian. I'm going to share my screen. Right. Bear with me. All right. One of the big changes we made in the Jetty release is we transitioned from Qt5 to Qt6. This is a pretty major change, and we wanted to take a moment to kind of go through what you need to do in this transition. And in fact, it's not most of the changes are transparent to you, but we want to just give you a little bit of detail there. So Qt5 went EOL end of life in May 2025, and so in order to get the latest updates and features and bug fixes, we were had to upgrade to Qt6, which came with a bunch of changes, and a lot of people worked on this. It was a big team effort and it took over a year. and but we're happy to say that it's over. And the one thing that was kind of something we had to change, we had to break, is regarding plugins. And so if you are a Gazebo GUI plugin developer, so if you've made your own plugins, you'll need to make some changes. But thankfully, that's very minor. We have a migration guide up for you on this link, and we'll share the slides after the meeting. But the main sort of change is that if you're referencing C++ objects from your QML file, and they are, as you see, uppercase letter, they start with an uppercase letter, the word screenshot here, Qt6 doesn't allow that. It doesn't allow uppercase letters to be objects in the QML. I won't go into the details of that. So we had to make it start with an underscore. So there's a prefix there, so you'll have to go and search and replace your QML modules and add the underscore there. And this is not a critical change, but you'll also notice that you don't have to put any version numbers when you import QML modules. This is a new thing in Qt6. Basically, if you leave it out, it will import the latest QML module, and that's what's recommended to do. And if you when you're transitioning to or migrating, if you have some version numbers in there, it may not work because it might be referencing a really old version. So I would recommend removing them. Most of the things are, they should look very similar. There might be a few little different things. As you can see here, the panes, the little cards, there's like a little gap in there that tells you that this is how we've been telling that this is Qt6. But there's a few other things. I think the spin box and the tree view had to be rewritten because of deprecated modules in Qt6. And so if you use those directly, you'll have to go to the Qt6 migration guide, upstream Qt6 migration guide, and learn about how to migrate. And that's all I had. Thank you.
All right. Awesome. Yep.
Right?
You're also next. All right. You want to talk about the standard simulation interface?
Yeah. All right. The standard simulation interface is a ROS package that was created leadership of Adam Dabrowski from Robotech to basically allow multiple simulators to be interchangeable, and then you can actually control the simulation from ROS without changing your code. These are a set of services and actions that allow you to just talk directly to the simulator, and it's a standard that we're pushing forward with. And today I would like to show a demo where we use a set of some of these services. We'll use a service to spawn objects, to reset simulation, and to set the state of an object in the simulation. When we spawn objects, Gazebo supports spawning from files or SDF strings or from fuel. Here we'll show from fuel. And basically, this is just to show what you can do. It's not a very, sort of practical example, but it just shows that what can be done. It's a simple conveyor belt setup where we will spawn a few objects onto the scene here on the tray, and we'll set the velocity of the tray so it moves towards the robot. The robot has a camera, it will scan it, and it can be part of your test routine or your machine learning setup, but it could be anything. And for conveyor belts, this is probably not the best way to do it. I just wanted to show that you could set velocities of objects, and so this is running in ROS, and I'll start the node here, and I'll just spawn these objects and run them and it'll move towards the robot, and you'll see how it does. Part of the work here involved finding the bounding boxes of these objects so they respond in without overlap. The simulation, the standard simulation interface has an option for simulators to implement that, so you can query that. Gazebo doesn't implement that, but I have provided a script that would actually use Gazebo to compute these and output the dimensions of the bounding boxes of the objects. We'll have that in the Jetty Demo website or a GitHub repository after this, and it's using the Python API, so it shows that another feature of Gazebo as well. And yeah, this will just keep on reset and going into reset and running the simulation over and over again. And that's all I had.
All right, thank you, Adisu.
Going a lot smoother on my machine than on the GVC. Google View.
Awesome. So if you want to find out more about standard simulation interface, there's actually going to be a ROSCON talk this year. We're doing the joint talk with the NVIDIA, Isaac Sync folks, and also with Robotech OCDE to show what you can do with these powerful standard interfaces. All right, now is actually back to my turn. Let me share my screen. All right, so I'm going to do a demo of a new physics feature, actually a new improvement to existing physics feature, and that is the automatic inertia computation. So some of you may already be familiar that there is the ability for Gazebo to automatically calculate inertia for you. However, there's a limitation that users have to specify the density in order for auto computation to work. So just for example, if you look at these cordless drills here, I guess for people like me, it's difficult to specify what the density of a drill is. I may have to look it up to see what material it is and then find the right number to specify. But however, it is more intuitive, at least for me, to know the mass of a cordless drill. So we made a quality of life improvement that now when you want to automatically compute inertia, basically all you need to do is just specify the mass, and then you have to set inertia to true. Just an example here, we have demos of 3 cordless drills. So the one on the left is, let me show the SDF here. Basically, typically, this is what you see in a lot of SDFs where you have a model, a link, and a collision, visual, etc. But there's no inertial tag here. So if you don't know already, by default, Gazebo uses default inertia matrix, which isn't always the right thing to do. So if I visualize inertia here, it's going to show this pink box. And what that is that by default, Gazebo uses a 1 cubic meter inertia representing 1 cubic meter box here. So as a rule of thumb, the visualization should roughly match the size of the geometry, which in this case is the drill. And you can see here is kind of far off. Let me just disable it now. But here, what I see you in the middle here, we have this the drill with this particular SDF. So basically right now I just say inertia. I added an inertial tag and say auto equals true to tell it to automatically compute inertia values. And I just give it a mass. So as a rough estimate, I give it 1.5 kg. And then compared to, so this will be the new feature here, and compared to the one on the right, where I have a manually specified inertial parameters. So this model has been on field for a while, and this is the drill that we've been using for many of our demos, etc. So it has all the inertial matrix that has a post offset, and then also a very specific mass here. If I turn on inertial visualization, here you can see the inertial values kind of match each other. So the one in the middle did a pretty good job of estimating the inertial values just based on mass itself. And then this works for meshes as in addition to just simple shapes. And right now I am just going to disable this. So I'm just going to show you what happens at runtime, the physics behavior. So what I'm going to do is I'm going to publish a message to detach, to drop these drills, and then we'll observe the physics behavior of these drills with different inertia values. All right. You can see the one in the middle and the one on the right is settled relatively quickly and stabilizes. So with good inertia values, the physics is stable. But however, on the one on the left, if you just left it without specifying any inertial values, you can see it's kind of off. It still continues to wobble because of, and the behavior looks unnatural. So I guess some tips to remember in the future. If you don't know how, if you are unable to get an accurate measure of your inertial values of any objects that need to be dynamic, you can try out this auto equals new feature and just give it a mass. And that's this new physics feature. All right, let's go to Arju. Would you like to talk to us about machine learning, reinforcement learning?
All right. Hello, everyone. So for this demo, I'm going to move away from that world. This demo is just a very simple thing. We have spent some time kind of identifying how to improve our Python interfaces for reinforcement learning. And so in this demo, what we have is the hello world of most reinforcement learning algorithms, which is the cart poll. And so you can, okay, it crashed during demo. But the key thing here is we have this system here. You can use Python. You can use stable baselines theory, which is a common reinforcement learning algorithm. We have fixed the text fixture so that you can reset it. And we provide you with convenient APIs so you can do this all in Python. Since the demo crashed, I am going to, for unrelated reasons, I am going to do something else and share a pre-recorded version of it. Because let me just quickly share a pre-recorded version of it. It's not super impressive, but you can see it. So here is a trained model. The idea is that the model has to the model has to keep the cart hold upright. So you can see this happening after a few iterations of training. You get this kind of behavior. It does. So you can try it out. It should not crash for you. I think the crash was due to something unrelated. Yeah. Okay. So that's reinforcement learning.
All right, you got a lot of live demos. Video backups are essential. All right, so we're continuing with Arju again. So he's gonna show us export occupancy grid feature. Go ahead.
So moving back to the demo world, let's go to the demo world again. Let's see if this shows up. Yeah. Okay. So moving back to the demo world, we have this. We often have situations where we might want to export an occupancy grid. Maybe we want to like do some work with nav2 or say some type of banner we have. So we now have a feature which is going to be merged very soon. This UI is not in Jetty yet, but should be there soon. Where you have this kind of thing, you can specify the type of LiDAR you have, the kind of parameters. So for instance, if your robot has a LiDAR placed 0.5 meters from the ground, any type of like other quirks of the LiDAR, you can specify like, okay, like I want a grid of, a certain size, and then you can just set this up, add probe, and you can click start scan. This is going to take a bit of a while because immediately, like the demo was pretty heavy, and this computer is a pretty old computer. But just give it a few minutes, and we should be seeing some output. See. Yeah. Okay. So there we have it. And so you can see that you get this occupancy grid exported from automatically exported from Gazebo, which you can then save somewhere and use it for your own. Okay, the save window's not showing, but you can save it and use it somewhere else, either for localization or for planning or something else. So that's the occupancy grid export feature. I think back to whoever's next.
Yep, thank you. So I guess we'll be using this grid later on in another demo that Arjo exported. So yeah, by the way, this is a new system that comes with Jetty. You launch it, and you should be able to just use this system, provided that you specify in your SDF. And the one I just showed is the GUI for configuring the system in there. So those will be about that GUI. I believe the GUI will be available soon, right? Okay. All right, so let's go back to me. All right, so let me share my screen again. All right, so I am going to show another feature. This is a new plugin that comes with Gazebo as well. So this is an improvement to an existing plugin. It's called the wheelslip plugin. So the Gazebo has a wheelslip plugin for a while, basically. What it does is that applies some longitudinal and latitudinal slip compliance to the wheels of a wheeled vehicle. And basically you can configure slip and friction, etc. So however, that's fixed because there's some limitations. The slip values that you configure, they're always fixed. So imagine if you have a wheel robot navigating environment on top of different surfaces, you want these slip parameters to change as the robot moves from one surface to another. So what we did is that we added extra capability to this plugin to allow users to dynamically change the slip compliance values. So to demonstrate this new capability, we introduced a new plugin. It's called the Lookup wheelslip plugin. What it essentially does is that it uses a lookup map. We call it a slip map that represents the environment or the terrain that the wheel robot moves in. As an example, we just want to show this demo of the robot climbing a ramp. The effect, you see the slip effect becoming more obvious and evident when the robot starts to accelerate and climbs uphill. So here for this environment, this is the warehouse environment that we have. This is a top-down view. And basically I have this, I'm just going to show this here. I have this slip map here of the environment. This is the floor of the warehouse, right? And we encode the slip and friction adjustments in the RGB channel of the slip image. In this case, the green encodes the longitudinal slip value. So I added some slip here in this right corner, which corresponds to, let me make this transparent here, to this patch over here. I basically just overlaid texture onto the environment just to visualize where the slip region is. So what I'm going to show you is that I'm going to move the robot and then see what happens when it moves into the slip region. And then I'm going to publish a message to move the robot, and I hit play. The robot will start moving up and climbing up the ramp. So, right. So as as it climbs, there's already some slip happening. But as soon as the robot moves into the region, this is a front wheel drive, by the way. You see that the front wheels are slipping more and more. It's rotating faster than the rear wheels. And when both wheels enters the region, you can see we can see significant slip happening on the robot. So if I just move this robot out of the slip region, it's going to continue and move as usual. So this is the new capability that we added. We imagine that, so for example, you're out there creating a world, you have a terrain. So this works with height maps as well. So you have a workflow where you set up a texture for different parts of the terrain, like grass, asphalt, or whatever. You can just use the same texture map, convert it, just change the RGB channels to encode the different slip and friction parameters. That way you have a more streamlined workflow for configuring slip properties of wheels. All right, this is my demo, and I am going to introduce you to Saurabh, who's going to talk to you about another new plugin, Gazebo. Saurabh, whenever you're ready.
Thank you. Let me just share my screen. Yeah, so I just have a small presentation. This is about the DriveToPoseController. That is a new system plugin in Gazebo. And so the DiffDrive plugin in Gazebo receives velocity commands on CMD well topic and converts them to individual wheel velocities to move the robot model. However, if you want the robot to reach a specific pose, you currently need external controllers or planners to compute these velocity commands. So the DriveToPoseController addresses this gap. So it listens on the CMD pose topic, which is a new topic that comes up that is brought up by the plugin, and it uses a pose v message type, and a proportional controller inside the plugin computes the velocity commands required to reach the goal pose, and publishes them on the CMD well, which is brought up by the DiffDrive plugin. Since it's a proportional controller, it works by minimizing an error by reading audiometry from the post topic that is brought up by the audiometry publisher plugin. So at the end of the navigation, it publishes an acknowledgement on a reached post topic. So this plugin works together with the existing DiffDrive plugin, so DiffDrive plugin executes the velocity commands, the audiometry publisher plugin provides the robot pose, and both in place, the DriveToPoseController can be just added as a drop-in system. So in short, this controller allows robots in Gazebo to be driven directly to a pose without the need for a full navigation stack. It's particularly useful for demos, prototyping, testing, and the gains for the controller and tolerances for the distance and orientation can be configured as needed. So it's just how it works. So receives a pose, publishes a velocity command, consumes audiometry to minimize error. So let me just show a small demonstration of this now. So I'll be running the demo world, which is not the Jetty demo world, but this is a demo world present as an example for the DriveToPoseController plugin. So this is also a small warehouse environment with a robot at one corner. Now I'll be publishing a command to the robot. Let me just get my command. So upon receiving a pose, the robot will start moving towards this point, which is its goal location. And once it reaches that point, it will orient itself in the preferred orientation that we have provided. So then let me just show another command. This time it'll just move to another position over here. And maybe one more command to just move it to the other corner. So as you can see, it's a three-step process. First, the robot orients itself towards the pose, so it changes its heading angle. Then it translates towards that position, and then when it reaches, it orients itself towards the configuration provided as part of the pose message. So let me just switch back to the presentation now. So this was just one part of the work that I did, and now I'll just move on to the next part, some recent updates to the Gazebo command line interface. So a major change has occurred in the Gazebo ecosystem with the modernization of the command line. Historically, Gazebo CLI was Ruby based. Now we are moving towards now we are moving towards a more like a fully native C++ architecture. So this makes the CLI much simpler, more maintainable, and cross-platform. Previously, the GZ command came from the GZ tools package, where each subcommand like sim, topic, etc., was a Ruby script that passed arguments and then called into C++ through external bindings. That meant we had a mixed Ruby and C++ stack, which worked but brought a lot of drawbacks. This setup made debugging hard, as tools like GDB or Vagrant couldn't see through Ruby. On Windows, especially the fork model that was in the Ruby script didn't work so well, so commands like gzsim wouldn't run properly. And developers also had to maintain logic split across Ruby and C++. And the result of this was poor introspection. It was tricky to debug, painful to change, not cross-platform, and it was incapable of containerization. The solution was to redesign everything to a native C++ approach, where each subcommand like gzsim, gztopic, gzservice is now a standalone binary with its own argument passing and logic. The Ruby wrapper still exists, but it only forwards calls. No more external calls and no more core Ruby logic. So as you can see, so with GZ tools, you can use a gzsim --help command to launch the executable, but without GZ tools also, you can just directly use the executable by passing in the arguments. So now you can run gzsim directly and debug with GDB, all without Ruby or GUI dependencies. So for users, the behavior stays the same, but internally the CLI is much more robust now. So just a difference in the two old CLI versus the new CLI. We have tried to keep the experience as similar as possible. The only thing that you can notice is that there will be a usage where it will be pointing to the executable that is actually running. So if you don't want to use GZ tools, you can just manually run this executable and use gzsim. So that's it from me. Thank you.
All right, thank you, Salar. Okay, now we move on to Nate, who's going to show us some performance improvements on loading assets.
All right, thanks, Ian. It is not showing. Oh, it is showing my screen. Great. Okay, I have. Well, I thought I was going to have a really boring demo, but I think Adisu might have beaten me with a Qt5 to Qt6 presentation. Anyways, So this ideally is going to demonstrate something that you never see, but should hopefully make your life a little bit better when you're using Gazebo. Fuel has been mentioned a couple times in this presentation, but just really quickly, this is Fuel is an online asset repository that we've been using for a number of years. And it's grown quite large, and depending on the simulation assets you use, the world can be kind of complex, potentially loading hundreds of different types of models. And ignoring your internet connection, this could take multiple minutes. And we've seen situations where people try to run simulation and they stare at a screen wondering what is Gazebo doing while it's slowly downloading models in the background. So we thought we could improve that experience for everybody by doing something relatively simple, moving away from a sequential model download to a parallel model download. So now the default behavior with Gazebo Jetty is to run a background worker pool to automatically download simulation assets in parallel. And hopefully you never notice this, but it should reduce your wait time. So to really quickly demonstrate this, I'm currently sitting at the cache location where Gazebo will download model assets. And I just want to prove to you that there's nothing here, so I'm not going to cheat. I've put up the Gazebo Jetty demonstration world on Fuel, so you can go and run this if you feel like it and just download things from Fuel. For those familiar with the command line interface, I'm just going to run the server for one iteration and time it just to give you a sense of some performance improvements. This overall is not a huge world compared to some others that we've done in previous competitions like Sub-T, but it's sufficiently large that you'll see a time difference. So this took 8 seconds for me. I've done this a number of times, and this roughly between 7 to 10 seconds it'll take to download this. And to prove that something actually downloaded, we have 106 megabytes here. Awesome. So that took only 8 seconds to download the Jetty Demo world. I'm just going to get rid of everything here. This is clear now. And if you want to go back, we do support the old behavior. So if you feel like waiting, patience is a virtue. You can add wait for assets. And now you'll see sequential downloads. And this will take a little bit longer. This will be the behavior that happened in previous Gazebo iterations. Wow, before this took around 20 seconds. Now it's taking much longer. Here it goes. All right. So this kind of demonstrates we can use threads in Gazebo. Excellent. That is about all that this demo has to show. This should be fairly transparent to people. This, in this case, took 30 seconds. That's the longest. And it's actually the same amount of data here. All right. That's my exciting demo, and I can hand it back to Ian.
All right, thank you. Now, thanks to you, we cannot go on coffee breaks while we launch Gazebo. All right, let's go to the next feature, which I'm pretty excited about. Zenoh, do you want to take it away, Carlos?
Thank you, Ian. Hello, everybody. Yeah, I'd like to present some exciting new features in Gazebo Transport. I'd like to start saying that Gazebo Transport is one of the key pieces in the Gazebo ecosystem. We use it everywhere. For example, in Gazebo, it's used in combination with the entity component manager, it's used to interact with the different pieces in the simulator. It's used to, especially when you want asynchronous communication, it's used to communicate between the server and the GUI, or also to interact from the outside world with Gazebo. It's essentially a pops up or request response interface. I'm simplifying, but this is essentially what it is. And we started this project back in the old days, more than 10 years ago, and it's essentially a combination of our own custom code plus a few dependencies. ZeroMQ is the main middleware dependency right now, and also Google Protobuf. So ZeroMQ was chosen 10 years ago because it was a very active project, a project with a lot of traction. And they define themselves as sockets with asteroids. So that was the building block that we used to to create Gazebo transport on top of it, and it serves. It's been working very well, but ZeroMQ hasn't been it's not very maintained these days. It doesn't have the same amount of users, tractions, etc. So something that we typically do in Gazebo, in the Gazebo team, is also look around, and we take a look at other dependencies, and when they are very active, we try to integrate them into Gazebo. And Zenoh is one of these dependencies, is one of these middlewares that we looked at it. The ROS team also looked at it, and it looks very good. So we decided to integrate it into Gazebo Transport, and this is what's been implemented in Gazebo Jetty. So the type of API, it's the same. You're not going to notice any difference, but you can set this environment variable GC transport implementation at runtime if you want, and you can switch between ZeroMQ or Zenoh. It's your choice. ZeroMQ is still the default middleware, but we're optimistic about it. So if everything goes well, probably like the next release we'll switch, and then we'll use Zenoh. What are the main advantages? So essentially, as I said, we created Gazebo transport, with our own code. So we had to create our own discovery code, our own discovery protocol to figure out when there are new publishers, when a new subscriber comes up, when a node drops, etc. And this is far from ideal, right? Ideally, we rely on a middleware that has its own protocols, their own. We don't have to maintain it, essentially. So that's one of the main ideas. It's also more configurable. So ZeroMQ relies on UDP multicast, and in the case of Zenoh, it's very easy to configure with configuration files, and it also supports many other different topologies, not only UDP multicast. It's a very active project, as I said, and one of the other advantages is that it's very aligned with ROS2. In fact, we try to follow the same conventions all over the place, and that ROS2 uses. So ideally, eventually we might converge, and we might be able to talk when they support Google Protobuf, probably. It's all not advantages. So one of the main disadvantages here is that it's less tested. This is just fresh from the oven, and it's less optimized for now. It's something that we'll continue looking into. And then just to show you a little bit of it, I like to show you a very simple example. It's just a publisher publishing messages on a topic using Zenoh. And then here is just the subscriber. But the nice thing about this subscriber is that it doesn't use Gazebo transport at all. It's just using plain Z++ code using Zenoh. And then nothing fancy here, but it's able to subscribe. So this is just to illustrate what I mentioned here, that there's nothing related with custom discovery, custom protocols, or anything like that. In fact, if we look at the code really quick, the only thing that it does is creating here a Zenoh session. We don't need to understand the whole thing, but it's just creating a Zenoh session, a callback here, and then we just declare a subscriber here, passing the topic and the callback. And then in the callback, the only thing that we do is get the attachment, which is a Zenoh concept, where we encode essentially the type of the message that we received. And then we use GC messages factory class to create an empty message of that type. And then what we do next here is just we use the serialized data that's into the message, and we unserialize it into the new message that we just created. And then we finally print it. So just an example to show you that there's no magic here on top of that. We just use directly what Zenoh offers. And then finally, an initial benchmark. Main disclaimer here is that this is completely preliminary. Zenoh is not as optimized as ZeroMQ right now, but we wanted to give you a first taste of it. The first two plots on the upper side are what happens, or experiments related with latency and throughput in the case of intra-process. So when publishers and subscribers are on the same process, you can see that it's comparable. So nothing the two middlewares are the same here in the case of latency, and then in the throughput, besides one outlier here, it also looks pretty equivalent. And then the two plots on the bottom are inner process examples. One measures latency and the other throughput. Lower is better in the first plot, and higher is better on the second plot. So in this case, SystemQ is the winner. It seems to receive messages with lower latency. And then on the right-hand side, the Zenoh seems to have higher throughput. So I just wanted to send a message that for now we consider them equivalent. We don't see a clear winner of it yet, but we can start using it and improving it. That's all I had to say. So I'll hand it over to Ian.
All right, thank you. This is an exciting feature that we'll be pushing and doing more work in this area. All right, let's go to Steve Peters.
Thanks,
packaging.
Ian. Can you hear me?
Yes.
Great. Hi, everybody. I'm going to present a quality of life improvement for Jetty. And this is going to be the most risky thing possible, a live demo, and I'm going to try to make it interactive. So start off with, I want to review how to use gzmath Python bindings. So if you do it wrong, you get an error trying to import. So does anyone know what is the major version of Gazebo math in harmonic? Anyone? It's 7. Boom, it worked. Does anyone know what the major version is in ionic?
10.
It's 8. Does anyone know what the major version is in Jetty?
10.
Who cares? You don't need to know. Not anymore, because we removed the version numbers from package names in Jetty. This simplifies a lot of things. The CMake find package logic, CMake target names, specifying dependencies in package.xml files. It also enabled us to provide Python bindings for the Gazebo ROS vendor packages, and Jetty is currently enrolling. But one trade-off is I was able to do this demo right now because I have Harmonic, Ionic, Jetty installed side by side. But the trade-off is that future versions of Gazebo will not be side-by-side installable, starting with Gazebo Cura in the same prefix. But you can still use containers, you can use Colcom workspaces to get multiple versions of Gazebo on a system. We think that's a reasonable trade-off. For more details, take a look at the post we made on Discourse, which yeah, I'll tell you more about it. That's all I have.
Thanks, Steve. It looks like a simple change, but it's actually a lot of work on the behind the scenes.
Yeah, and it'll save us, save the maintainers a lot of time. There's a surprising amount of churn involved with maintaining that.
Mm-hmm. All right, continuing on with the same thing of build packaging and build systems. Let's go to Shamik. Would you like to talk to us about Bazel?
Hey everyone, my name is Shamik and I work for Intrinsic as a simulation engineer. I'm working closely with the Gazebo team. And today I wanted to talk to you about, and let me see if I can share my screen here. Okay. All right, Bazel in Gazebo. See, if you don't know what Bazel is, it's a build system alternative to CMake with a focus on fast and reproducible builds. What you see here is a simple client program built with Bazel that spawns a model, waits for it to settle, and then removes it and respawn it. The server side itself is running from a binary release here on my Mac OS. So switching to the source code here, what you see here is the C++ client. It should seem familiar. What we're doing here is to set some command line parameters. We have a simple connection class that talks to the Gazebo sim server over GZ transport to make sure it's running. And finally, we have a spawn controller class here that does this loop of spawning over GZ transport. It's using the existing user command system in Gazebo to spawn the model. we pass it an SDF file, and it listens to the velocity of the object from the server and determines when to respawn it. If we look at the build file here, you'll notice that first of all, there's no CMake. This is the Bazel build file, and you see a simple binary target here that configures the executable. The important thing here is that you see all these dependencies. So Bazel ships with its own dependency management system. It's called Bazel modules. And if we look at the specification there, you'll see that we have the pre-release versions for Jetty listed here for the different packages. We have uploaded the pre-release versions for Jetty, but also the Ionic packages to the Bazel Central Registry. So this is available already to try it out right now. And we plan to upload the Jetty release packages soon. So yeah, that's pretty much it. The main caveat here is that we don't have the GUI components here in the Bazel build yet, so there's some work in progress. This was made possible by a long tail of effort from the Gazebo team over many years, including starting from Bazel workspaces, but then porting it over to bzlmod. And we'll make this example available as a tutorial in recent future. Please give it a shot and let us know how it works for you. Thank you.
Awesome. Thanks, Shamik. It was a lot of work to package all this. We also had to package all the dependencies as well, like free image, bullet, dartsim, etc. And we uploaded all of them to Bazel Central Registry. All right. And now, last but not least, let's go to Aaron, who's going to show a more complex demo with OpenRMF plus Gazebo.
Thanks, Ian. Let me try to present. This should be it. Yep. So my name is Aaron. I work at Intrinsic and I'm part of the OpenRMF PMC. So obviously I'll be talking a little bit about our efforts in OpenRMF integration with this current Gazebo release, as well as the world that came with the demo, essentially. So a little bit of how it will look like eventually when I start it is, maybe I'll just show it at a live demo later. But a little bit of recap of what OpenRMF is. It's a multi-robot framework that is built with ROS2 and Gazebo in mind to allow multiple fleets of robots to share resources. And the resources span across like navigatable space in large deployed areas, infrastructure like doors and lifts, or hardware interactions like dispensers, ingesters, and work cells in this case. So I'll just start with the demo in this case. Okay, yeah, it should be this one. All right. So this is part of the demo world. I have basically, because we are actually, we are not running nav2 robots. We are running like plug-in robots that basically apply forces to move the robots like around the world. So I've been able to crank up the sim RTF in this case. So we see here how we've drawn out the OpenRMF navigation graphs. There are a bunch of what we call work cells, which are these stations. And this scenario is in the case where we need to move materials between stations, and it could be in any order in this case. And that's what we're going to demo essentially. So the first, we will send one of the robots in sequence, like 1, 2, 3, and then we'll send the other robot 3, 2, 1. So the reason why the graphs drawn up like this will become apparent quite quickly. So in these sort of complex scenarios, OpenRMF would negotiate between like all the different robots on how they should avoid each other as well as shared spaces. And in this case, there are dead ends. There are places where perhaps it's difficult for two robots to squeeze into. And we have plenty of strategies to allow like robots to navigate around each other in the scenarios like this. So in this case, I am just gonna ask them to keep running for like more than 10 loops, and they would be able to do this like without any issues, as long as they follow certain rules that I'm gonna talk about later on. Okay, so I guess in this case, the live demo kind of works. I'm just gonna go back to slides. This one. Oh, sorry, I did this. Okay, I can skip this because it worked. One of the features that we use for this integration is actually the occupancy grid generation. So I work with Arjo to get this out. So generally in OpenRMF, we would use the floor plan of the site to build out the digital twin and build out where the robots can or cannot navigate. In this case, we directly use the generator occupancy grid. There are some issues regarding like scale, origin of where the map starts and all that, but the traffic editor, the RMF traffic editor, has the tools required to do the offsets and stuff. So like for now it works. Yeah, it kind of looks a little janky, but it still allowed us to draw up all the navigation graphs that's necessary. So back to the strategies that we employed. In factory floors or warehouses, in this especially that looks like the current demo world, normally companies would deploy like AGVs, especially if it's a factory that has a lot of people around. They'll draw up like safety lines and all that. Instead of they use AGVs instead of AMRs because they need a specific flow, certain rules and all that. And in OpenRMF, we can do some of that as well. So one of the few things that we did with the world just now was that to enforce unidirectional lanes. So one lane would be responsible for going like to the left, the other one to the right, and they're connected in certain places. What we call mutex groups. So most of us will be familiar with what mutexes are in like asynchronous programming. So in this case, it kind of works the same way as well. These are all the waypoints where only one robot is allowed to move and enter at any point of time. And in this case, these would be interacting with like the work cells in this case. So that means that only one robot will ever really be in this vertical line that would enter or exit this particular dead end. Next one would be like holding points. So this would allow buffer zones for all the AMRs to wait before actually entering the mutex groups. And then this is one way that we can allow multiple robots to keep on going around each other in this kind of complex scenarios. We do have another project in the OSRA, which is called Nexus. I won't talk too much about it, but the concepts are very similar, where we explore integration with AMRs and lots of work cells and how they can work with each other. So what's next? Oh, okay, I didn't remove the graphics, but essentially, one thing that we did not manage to integrate in time would be to look to use the DriveToPoseController that Saurabh presented earlier. So this would allow us to bypass using all the force control that we are currently using for our simulation plugins. And this would help us significantly scale up simulation with a lot more robots in a single deployment. And the next thing would actually be looking at the next generation OpenRMF, which is what can be that we can craft into what we call workflows. So this allows us to introduce a lot more complicated behavior instead of just asking robots to go here and there and interact with different systems. For those that are interested, there is the interoperability working group or special interest group that Gray actually manages. He's the PM. He's also part of the PMC for OpenRMF. And then lastly, we would probably look into updating like what we are doing with Nexus with all the different, I guess, the improvements in this current Gazebo release that we can help scale up the simulation size essentially. Yep, that's all. Back to you,
Awesome.
Ian.
Thank you, Aaron. It's a great demo. Awesome work. By the way, they only have like less than a week to put this together, and then they managed to do it. So that's all the demos we have for today. So altogether 14 of them. I'd like to thank all the presenters. Basically, they spent a lot of time just making use of the new features while also working on the release and then putting these demos together. Especially for the folks, there are 3 here from Singapore. It's right now 1 a.m. their time. They're staying up just to show us, all these demos and everything working live. All right, thank you. I will hand it back to Adisu. Would you like to say any last words?
The only thing I would like to say is to reiterate that we really would like to hear from you. So please go fill out that survey. It will close in a couple of days. So just let us know how you use Gazebo, what's painful to use, what you'd like to see changed, what new features, what bug fixes, etc. So we want to hear from you. So. I think that's it. Thank you, everybody, for coming, and have a good one.
Bye.
Ciao.
See you, everyone.
Bye-bye.